Hello and welcome to the presentation of our work coined GNN-based control flow attestation for embedded devices. We did this work with our colleagues from the Technical University of Darmstadt, NVIDIA, and the University of Southampton. But first of all, why do we even need control flow attestation? Over the recent years, we saw a steady increase in remote code execution vulnerabilities, but also at the same time an increase in IoT devices worldwide. And this leads to an increased exposure to code reuse attacks in these IoT devices with low security. So some background on control flow attestation, CFA. What is control flow attestation? In the most generic and high-level way, we have three parties: the verifier, the prover, and the third party. And the third party wants to be sure of the state of execution of the prover. So it goes like this, that the verifier sends an attestation challenge to the prover and asks it to provide evidence of his state. The prover is computing or collecting this evidence and then returning it to the verifier, where the verifier is verifying this evidence, for example, against the database of matching evidences or through other means, timing, and so on. And then the verifier is disseminating a report, which is most of the time signed by the verifier, which shows the third party the state of the prover. For example, if it's benign, if the computations are correct or not. So also some background about code reuse attacks. I stated them earlier, but what are code reuse attacks and what examples are there for code reuse attacks? Here on the right, you see a control flow graph, also called CFG. And this control flow graph has two different benign executions. For example, the green one from V1 to V7, but also the violet one from V1 to V7 over different nodes. And return-oriented programming attack, also called ROP attack, adds extra transitions to this control flow graph. As you can see here, from V1 to V7, the execution has basically the same start and end point, but it is jumping from V6 to V3, for example, to create malicious functionality, which is not in the initial benign control flow graph. On the other hand, a data-oriented programming attack, or also called DOP attack, reuses the benign transitions, but still alters the control flow, but not the control flow graph. So as you can see here, the execution goes from V1 over V4 to V7, and the first part is reused from the green execution, benign execution, and the second part is reused from the violet benign execution. So we come to the related work in this scenario about control flow attestation schemes. You can divide them in three topics. Control flow attestation schemes relying on a complete control flow graph as a reference, on them relying on the memory access to the memory content, and relying on custom hardware. And the problem is that having a complete control flow graph is a very strong assumption. It's sometimes not possible to calculate one. Access to the memory content can lead to information leakage, for example, between the prover when it's collecting the evidence and sending it to the verifier. So either on the way or on the verifier side, this information can be leaked. And custom hardware is expensive in design, and it's not applicable to off-the-shelf devices. Which brings us to our research question: is it possible to relax the assumptions by leveraging machine learning to not have to rely on these strong assumptions? So we looked into suitable machine learning techniques and chose graph neural network as a promising solution. And as evidence, we chose to collect basic block addresses of the execution trace This avoids information leakage to the verifier because we are only sending the program counter values. We then process the trace to an execution graph while extracting the features. And here we don't impose any assumptions about its completeness because it's just extracted from one execution trace. And finally, we extract per node embeddings from the graph using a graph neural network. And this way, we maintain a correlation between elements in the different representation, as you can see here in red, from the execution trace over the execution graph, and over the execution embeddings, there's a one-to-one correlation maintained. This is our key intuition. So this key intuition is then utilized by our approach called RAGE, which does not rely on complete control flow graphs, as I said earlier. We use unsupervised graph neural networks to relax this assumption, and this model we show that this model learns the execution patterns and correctly separates benign and malicious executions. It also does not leak any data to the verifier or on the way between verifier and prover, because we only collect program counter addresses. It is also not platform specific, as we will show later. It can be run on any platform which has a TEE. And we don't need any extra hardware. We also don't need data labeling on the machine learning side. It is very lightweight. The model counts less than 9,000 parameters and can run even on a Raspberry Pi, where I will also show evaluation later. And as stated for the code reuse attacks, the model can precisely detect ROP and DOP attacks, including real-world attacks which were never seen before. So we use variational graph autoencoder in our graph neural network approach, and variational graph autoencoders, or also called VGAEs, are state-of-the-art generative models trained to learn to reconstruct input graphs to output graphs. And we designed our custom encoder able to extract the latent features of the input graph, and you can say that the control flow graph behavior is therefore captured in the output embeddings. And this customized version of a VGAE is used in our approach, which I will explain in detail. So here on the right, you can see our encoder design using our custom encoder design, which consists of 4 graph convolutional layers, which vary in dimensionality from 15 to 48, connected by dropout layers for regularizing the training. And we selected the VGAE as a model of choice as it was matching our requirements. Specifically, through a phase of model selection, we designed our custom encoder, keeping in mind the trade-off between complexity of the model and performance of extracting these embeddings that are rich enough to capture the control flow behavior. And as I said earlier, the encoder counts of 4 layers with varying dimensions. Specifically, we increase the dimensionality for expanding the features we extracted during the feature engineering phase, and consequently, we reduce it slightly again to discard the most noisy features. Which brings us to our system overview. To train our approach, we trace the executed software, as stated earlier. This one trace is preprocessed into a graph representation, and features are extracted. This graph is then used to train the model, extract the embeddings, and tune the attestation threshold on the validation set. To attest an execution, the software is traced again, preprocessed, and forwarded to the VGAE encoder, which then extracts the embeddings, computes the distance between them and the training embeddings, and this distance is then tested against the threshold and the system discerns between a benign and malicious execution. We did a real-world evaluation on code reuse attacks. We extended the RIPE framework with a gadget length configuration option for testing different ROP chain length, and the RIPE framework is a collection of code reuse attacks, ROP attacks. We extended it also to include benign application logic to collect traces from additional software, and we chose to use software from mBench IoT dataset. And we tested this on a BeagleBone Black, Xilinx UltraScale Plus, and an NVIDIA Jetson device. And as you can see here on the right, RAGE correctly separates benign and attack traces in every case with a great distance even. This is because this RIPE framework attack is not stealthy. The ROP attack is basically not returning the execution flow back to the benign application, but is basically terminating the program and resulting in a shell. To also be able to evaluate stealthy CRAs, we simulated ROP and DOP attacks on benign traces by creating an algorithm which adds malicious traces which show ROP and DOP attacks in these traces to the traces. We did it this way that the control flow is always returned to the program, which, as I stated earlier, RIPE attacks don't. So these are more stealthy. We evaluated on 23 software, collecting around 1 terabyte of trace data on which we evaluated. Here on the right, you can see that the data sets we use are OpenSSL and the mentioned mBench IoT dataset. So as you can see, for ROP and DOP attacks, the F1 score on both sides is in the high 90 range, which means that we are able to detect even stealthy simulated ROP and DOP attacks, which are even more stealthy than in the real world. However, ROP attack is easier to detect as it creates new edges in the control flow graph, and DOP attacks are harder as it reuses benign edges. And this detection of the DOP attack also heavily relies on the extracted features, where we have also evaluation in the paper. So refer to the paper for this evaluation. We also evaluated different ROP chain length in the paper. So yeah, refer to the paper. Here in detail for the OpenSSL dataset, you can see that for both ROP and DOP attack, the distance of the benign ones in yellow and the malicious ones in blue is rather high, and it's and most are easy to detect. Finally, we also evaluated the performance. We used a Raspberry Pi 4B 2 GB version to show that the prover and the verifier can both be an edge device such as a Raspberry Pi. And on the prover side, you can see that the average trace step length is around 100,000 to 10 million. But still, the pre-processing time is only around 4 seconds. The processed trace size is only in average around 0.73 kilobyte, which is sent over the network. Here, you can also do the pre-processing on the verifier side, but then the whole trace needs to be sent over. So this is a trade-off between pre-processing on the prover or sending over the network. On the verifier side, the initial model training time only takes 5 minutes on a Raspberry Pi, which is feasible, and the inference runtime of the VJE model is only 0.005 seconds per execution trace. Thank you very much.